We have Vasundhara from University of Cambridge, and she's going to be talking about disk dynamics in protoplanetary disk after stellar flybys. So take it away if you want to. 3 minutes warning.
Thanks for the introduction. Hi everyone, I'm a second year PhD student at Cambridge, working with Christiana and Kathy Clark, and going to be talking to you about stellar flybys today. So just as some brief background, thinking about what sort of problem we're looking at here, we know that protoplanetary disks contain gas and small dust grains, micron-sized dust grains that need to grow to pebble and then planetesimal sizes to become the building blocks of planets. And we know how dust grains grow at very small sizes via collisional sticking, and we know how they grow at larger scales to get to planetesimal scales via gravitational attraction. But the key problem that I'm trying to, that occupies a lot of us in planet formation is how dust grains grow at these intermediate sizes from centimeters to meters. And that is what we don't fully understand. So we call this the centimeter size barrier. And there's a few reasons why we're not sure how centimeter size dust grains grow. There's most importantly, the radial drift barrier. So they should fall into the star much faster than they can collide together and grow. And they can't grow via collisional sticking because at those sizes, we expect them to fragment or bounce off each other rather than sticking together. So there's a few proposed solutions for how these dust grains might grow. And the most popular and promising is the streaming instability, which we've already heard a bit about this week. And very simply, the streaming instability is a drag-based instability. So it's based off the interaction between gas and dust. And so it reduces this dust radial drift. And what we get are these dust filaments forming. This is a shearing box simulation of the streaming instability. So we've got radius on the x-axis, basically, and azimuth on the y-axis. And what we get are these small filaments forming in the streaming instability that then lead to these clumps and the growth of dust over densities. And so we can concentrate dust together in these over densities and grow them to planetesimal sizes. But we only actually trigger the streaming instability locally in regions with a sufficiently high dust to gas ratio. So if we define the dimension of Stokes number as the ratio between the stopping time, which is that first factor, so that's the ratio between the dust grain density multiplied by the dust grain size S divided by properties of the gas, its density and sound speed, and the ratio of that to the local orbital timescale. And that gives us the dimension of Stokes number. So basically, it's a function of dust grain size and the dust's position in the disk, a particular disk. And centimeter-sized dust particles in a typical protoplanetary disk are going to have Stokes numbers of about 1, depending on their radius. And so we can see from this plot here, which I've adapted from Lee and Udin 2021, that at Stokes about 1, we need dust-to-gas ratios of about 0.005 or higher. So we do need the disk to have these long-lasting substructures, and they need to have high enough dust-to-gas ratios to locally trigger the streaming instability. And luckily, we do see that most disks have substructures. So just taking a little venture into observations here, we've seen from ALMA that we've got all these beautiful gaps, rings, spirals in dust disks. And the question is, can these substructures that we see concentrate dust enough to trigger dust grain growth and hence planetesimal formation via the streaming instability? And relatedly, what actually causes these substructures? We know that a lot of them are coming from planets embedded in the young disk and carving out these gaps and rings. But we could also have substructures by interactions with another star, a bound or even an unbound companion. And that leads me on to stellar flybys. So we define flybys here as a single parabolic interaction with an unbound companion. And just quickly briefing you on some terminology, we've got prograde flybys, which is when the orbit of the perturbing star is in the same direction as the rotation of the disk. And we've also got retrograde flybys, which is when the orbit is in the opposite direction to the rotation of the disk. And we also parameterize the flyby by its periastron distance, which is the distance of closest approach to the primary star. And we think that encounters with unbound perturbers should be fairly common for young stars and dense stellar environments. There's a range of estimates in the literature, but just as a rule of thumb, encounters within 1,000 AU, we might expect up to 50% of stars in young stellar clusters to have at least one of those encounters. And if the flyby is close enough, we can induce these tidally induced spirals in the perturbed disk. And so we've got evidence that flybys can produce these substructures in young disks. So the key question that I focused on in this work is, can the flyby-induced substructures act as dust traps? Can they concentrate dust to high enough dust to gas ratios to induce the streaming instability? And so I ran some simulations with Phantom to investigate this. So we've simulated 5 disks perturbed by flyby encounters, and then we also, importantly, simulated 1 control disk, which just sat there and nothing happened to it. And we've got a disk with an initial extent of 150 AU around a solar mass star. We use 10 to the 6 SPH gas particles and 10 to the 5 dust particles, and the dust grains have the size of 3 centimetres, which again corresponds to Stokes numbers of about 1 or slightly larger. And these are quite large dust grains, so we're going to be using the 2-fluid algorithm for dust particles. And also importantly, these are all coplanar flybys, so we haven't looked at inclined flybys in this work. And what we've varied in these simulations are the mass of the perturber, the periastron distance, so we're simulating some grazing flybys where the star comes quite close to the edge of the disk, and then a couple of non-penetrating flybys, which are slightly further out as well. And we've got mostly prograde flybys, but we also simulated a retrograde flyby. And so, on to the pretty videos, which everyone's here for, if they work. So this is a prograde flyby, and here we're looking at the gas column density. You can see that perturber coming in, and it's inducing these beautiful spirals in the gas disk. And then over time, we see these spirals smooth out and start to dissipate. And so by about 7,000 years after the flyby, the gas disk has been truncated, but we're not seeing evidence of spirals for as long. But if we look at the dust column density, it's actually a slightly different story. So here's exactly the same simulation, but the dust disk. And we see these spirals induced again, and they actually last for longer. And so we've got longer lasting dust substructures than gas substructures. And we can see even by 8,000 years after the distance of closest approach, we've still got substructures in the dust disk, but we don't have them as clearly in the gas disk, which is quite promising. So the next step is to think about what happens to particles within these substructures, and do they get high enough dust to gas ratios to trigger the streaming instability? And so to do that, we're going to select individual SPH particles. SPH is really useful for this because we can select these individual particles and follow them over time to see whether their dust to gas ratio increases. And so to select particles, what we're going to do is divide the disk into equal azimuths. I've shown 10 here, but in all the cases I'm about to show you, I used 50. And then what we're going to do is we're going to select dust particles within the substructures. And if we're looking at a gas spiral like we are here, we'll select dust particles with the highest interpolated gas density in each azimuth. And if we're looking at dust substructures instead, then we're going to select dust particles with the highest dust to gas ratio in each azimuth. And then we've got our set of particles to track, and we're going to just trace their behavior back and forth in time. So what actually happens? So as we saw, the dust substructures are much longer lasting than the gas substructures. And so for that reason, we're going to be focusing first of all on dust substructures. And here we've got that prograde simulation again, and we saw those spirals in the dust disk. So I've selected 50 dust particles from within that spiral. And then I can look at what happens to these particles over the course of the simulation. And this is their dust to gas ratio over time in red. And we've got more than an order of magnitude increase in the dust to gas ratio. That dotted vertical line is the moment of periastron. And then I mentioned that I ran a control case without a flyby, and that's the gray line. And so we're comparing these particles to 50 particles at a similar radius in the unperturbed disk, and they don't have this huge increase in dust to gas ratio at periastron. And so we can see that compared to an unperturbed disk, the flyby triggers this at least an order of magnitude increase in the dust to gas ratio for a prograde flyby. And so that's the dust substructures. What about the gas spiral arms? Are they as efficient as trapping dust? Well, we think probably not, considering that we saw those didn't last as long. So in some cases, we get dust growth in the gas spiral arms. So here's exactly the same simulation again, but looking at the gas spiral arms, and I've selected 50 different dust particles that are in those gas spiral arms. And we get some dust growth. You kind of get like nearly an order of magnitude increase again. Straight after periastron, there's a very sharp peak, which then falls down. That's basically a statistical fluke, so ignore that. But by the end of the simulation, we do get up to dust to gas ratios of unity compared to the no flyby, which still stays at about 0.1. And so, yeah, so we sometimes get this dust growth. I haven't shown every plot because I'm tight on time, but we get dust growth in the gas spiral arms in many fewer cases than we do for the dust substructures. So if I increase the periastron distance of the flyby any further than this, I'm not going to be seeing dust growth in the gas spiral arms. And we don't see it at all in the retrograde case either. So going back to the original question, are these dust to gas ratios in the substructures high enough to trigger the streaming instability? So here, once again, is this plot showing the critical dust to gas ratio required as a function of Stokes number to trigger the streaming instability. And what I've just shown you is that the dust particles in the flyby-induced substructures do have high dust to gas ratios after the flyby, and those dust to gas ratios remain high for many thousands of years. But are they sufficiently high to trigger the streaming instability and hence planetesimal growth? Well, let's have a look. So we know what the Stokes number of those particles that we were tracking is, and so we can see what the critical threshold required to trigger the streaming instability is, and then we can just compare that to that actual dust to gas ratio. So just as a quick note, what I showed you previously was this rho d over rho gas, and we're actually looking here at the surface dust to gas ratio. So I've just multiplied that by this factor, which is the scale height of dust and gas in the disk at that point to get this surface dust to gas ratio. And so we calculate the threshold value for each particle as a function of time and compare that to its actual value. And here we have that in the plot on the right. So this dotted line here is that threshold value of the streaming instability that we need to exceed. And we can see that right on time at the flyby, we exceed that value. We go up to about 0.1 surface dust to gas ratio, and that remains above the threshold for the rest of the flyby. The time axis here isn't in years anymore, it's in dynamical timescales at the location of the substructure. And we expect the streaming instability to be triggered about on the order of 1 dynamical timescale. So this is really promising because what we can see here is that the threshold for the streaming instability is exceeded for about 10 or even more dynamical timescales, and we only need 1 to trigger it. So yeah, the tracked particles' mean value of a surface dust to gas ratio exceeds the threshold for much longer than the timescale required to trigger the streaming instability. So what I've shown here is that we are definitely getting dust to gas ratios high enough to trigger SI. Gone a little bit fast, but this is my summary here. So like I said, we've got this open problem, the centimetre size problem in planet formation. And so what we need are these substructures that concentrate dust and promote dust grain growth. And we found that in these flyby-induced substructures, we have these very long-lived dust substructures, which definitely act as dust traps. The shorter-lived gas spirals do exhibit dust trapping, but not in all cases, just some. And the dust to gas ratios induced by the flyby are large enough to trigger the streaming instability. I haven't actually modeled SI here. I've just shown that we've got a dust to gas ratio high enough to trigger SI, and they remain high enough for long enough timescales. Thanks for listening.
Thanks, Ross. So we've got plenty of time. Oh, wow.
Thank you. Nice talk. You mentioned dust growth, but did you mean the growth of dust concentration or actual growth of dust size? Because I didn't see that in your setup, but maybe I missed it.
No, you're right. I mean that we've got dust to gas ratios high enough. By dust growth, I meant the growth of dust to gas ratio, because yeah, we haven't modeled dust grain growth at all.
Is it planned for the future?
Possible. It's a possible extension. Yes.
So earlier in the simulation, you showed where we see the dust. You focused on the substructures. I was wondering, because we see some kind of like contraction of the disk a bit. Is it like throughout the disk that you get like pumping of the dust to gas ratio, or is it like how much is it like outside of the substructure?
Yes, so I've looked at the total dust to gas ratio just on a very basic level as the mass of dust over mass of gas in the disk. And that goes up because of this dust contraction and the increase of dust radial drift, but not hugely. It's about, from recollection, about a 10% increase maximum. So yeah, so not huge.
Thanks for this very nice work. Yeah, it's close. Very promising. One of the things I'd be worried about a little bit is for the dust concentration that's outside of the gas spirals. Numerically speaking, in phantom, there's nothing that opposes dust concentration. And so in circumstances where you resolve the dust much better than the gas, it will just keep collapsing. And so some of that might be numerical. And so, I mean, you can do all sorts of conversion studies about that, but yeah, I'll take that with a little bit of grain of salt, because when you have concentration outside of those gas modes, the gas is not resolved very well.
Yeah.
And numerically, you're just going to keep collapsing because the dust doesn't feel any diffusivity or any pressure forces. So there's nothing preventing it from collapsing numerically.
Yeah, that makes sense. I mean, I haven't looked into it in detail and we haven't done convergence testing, so that's a very valid comment. Because we've got 10 to the 5 dust particles, I believe the dust isn't going to be extremely over-resolved, but that doesn't mean it's not over-resolved locally, as you said. I don't know if this is at all relevant, but we did run a simulation without drag, actually, just to see what happens to the dust in the absence of drag. So this is the retrograde simulation, on the left with drag at the end of the simulation and on the right without. And actually you do need drag, so this gas dust interaction, to maintain the substructures. Because what you can see is that they're much brighter in the case with drag, and when we turn drag off, they dissipate a lot faster and you don't actually get this endless dust growth. I don't know if that answers your question. Yeah.
So I have kind of like a dumb question, but it's because I don't know how about that information. In one of your plots, you show that the dust structure were like confined in a very small region around the star, while the gas is formed outside. Is this somehow related to how gas planets form in the outskirts of the disk and rocky planets form in the inside? Like, can that be explained by a stellar flyby, for example?
Interesting question. I don't actually know, because this is much earlier on in the planet formation process than gas giants actually forming. So yeah, really interesting thought, but I don't actually know the answer to that.
Very interesting work. I was wondering, you're considering 3 centimeter size particles. Presumably, if you go closer to Stokes, close to 1, so let's say millimetric or even smaller particles, this effect you're seeing would be even more dramatic. Could you comment on what you would expect if you were to consider a polydispersed distribution of dust? Because also in the context of streaming instability, that might pose a problem. I think there are some work showing that polydispersed in streaming instability are a bit hard to reconcile.
Yeah, it is a thing we've been thinking about, and actually I've started running a simulation with 5mm dust grains. So waiting to see how that goes. So it's in very early stages at the moment, but that is something we're thinking about. It's not polydispersed, it's just 5mm. But yeah, we would definitely like to see when the dust is more strongly coupled to the gas, how that changes our results.
Because you might even have higher dust to gas ratio, so that would
be even better.
Yeah.
Any other questions?
Just a quick comment that it's been in the code a long time that it is possible to do multiple large grain species together, and we've not used it very much, but it's a nice application.
Worth testing. Yeah, thank you.
2 more minutes, so it'll be all me, I guess.
Do you have an idea of the eccentricity profiles in your gas versus the dust disk? And does this, how is the eccentricity profile in the 2 disks?
I've looked at it and I can't actually remember what it's like off the top of my head. We didn't find anything very interesting looking at eccentricity. Actually, if you run this retrograde simulation for much longer, you start to get some growth of eccentricity in that inner cavity, but that's about it. We haven't really found anything worth commenting on eccentricity wise.
Any more? No? Quick question from me. So, what your results imply that if a star is sitting in a very compact environment, say at the center of the cluster or something like that, where there's going to be a lot of interactions between different stars, would you expect more planets to form in those systems? Like, is that observed, and can you check that?
I haven't checked that. That's a really interesting thought. Yeah, I mean, this is again early on in the stage, but yeah, that is, I suppose, the ultimate implication of these results. So it'd be interesting to check that.
Is there any observation or consensus that tends to be having more planets appearing at the more crowded environments?
I don't know about it, but yeah, no, that's a really interesting thought. Good to look into.
Anything else? If no more